Hello friends! Today we are going to talk about velocity and acceleration. Alright, so velocity is how fast something is moving, which is how its position changes with respect to time. So for example, a car drives from Orem to St. George, a distance of 265 miles. The journey takes 4 hours and 24 minutes. How fast was the car moving? Well, velocity is change in distance over change in time, which in this case is 265 miles in 4.4 hours. I divide those two and I get 60.25 miles per hour. But is that the velocity that the car was traveling at every moment in time? I mean, maybe the car did something like this. Here I'm plotting position as a function of time. Maybe the car started going at one velocity and then they stopped and they got lunch. And then after lunch, they started up again, but they travel at a different velocity. So when we take the total distance traveled in the trip divided by the total time that the trip takes, what we are getting is what we call the average velocity. But at any moment in time, the car may have been moving at a much different velocity. So, in other words, what we found is V average, the average velocity. Well, the average velocity is change in distance divided by change in time. If I want to find the instantaneous velocity, the velocity at a particular moment, what I have to do is I have to measure how x changes over a very short amount of time. So rather than finding how far the car went in that whole 4.4 hours, I would say, how far did it move in a second? Well, still, the velocity might have changed in a second. How far did it move in a millisecond? Okay, that's getting closer to the instantaneous velocity. The way that I get the instantaneous velocity is I take the limit as my time step goes to 0. How far does it move in 0 time, right? When we take that limit, of course, what we get is the derivative. So if I take the derivative of position with respect to time, I get the velocity. So here's an example. Later in the semester, we're going to study harmonic oscillators, and we'll find that things like a mass on a spring will oscillate, where the position of the object will just be some constant times sine of a constant times t. All right? So what is the velocity of our object that's oscillating according to this equation? Well, velocity is just the derivative of x with respect to time. So that's just the derivative of a sine omega t. The a is a constant, so it comes out of the derivative. And then if this were sine of t, we could take the derivative, but there's that omega in there. And so we're going to define u to be omega t, right? We're going to do the chain rule. And so I can write this as the derivative with respect to u of sine of u. I've replaced omega t with u, and then I have to multiply by du dt. And of course, the derivative of sine is just cosine, and the derivative of u with respect to t is just omega. And then I plug omega t back in for u, and there is the velocity of my object that is oscillating. So if x is a sine omega t, we took the derivative of that and found that the velocity would be a omega cosine of omega t. So in blue, I have the position x plotted, and in red, I have the velocity. Notice at time t equals 0, the position is moving, it's changing very rapidly as I step forward in time, and I have a high velocity, all right? But then, at some point, I reach the maximum displacement, and the object comes to a stop. So right up here at the top of the curve, as I move back and forth a little bit, the position doesn't change very much. So that's where the velocity is small. And right at the very peak, the velocity goes to 0. Then the position starts moving backwards. It starts moving back towards 0, and my velocity goes negative. All right? Then there's a point where, right where I cross 0, where it's moving backwards at its fastest speed, and that's where we see the velocity is the most negative that it gets. All right? And then it gets to its maximum negative displacement, and it comes to a halt momentarily. That's where the velocity crosses 0. So hopefully in this graph you can see the relationship between position and velocity. And again, velocity is just, the instantaneous velocity is just the derivative of position with respect to time. Now, if I know the velocity, can I go back and get x from that? If I know the velocity every time, can I find the position at every time? Well, let's think about this. Velocity is dx dt, which means that dx is velocity times dt. The distance that my object travels in a time dt is just its velocity times dt. Now, this is the instantaneous velocity, so we don't, and dt is infinitesimally small, so we don't have to worry about the velocity changing during that time dt. But if I want to find how far it moves in a finite amount of time, I do have to worry about the velocity changing. So the way I find how much it moves in a finite amount of time is I take these infinitesimal dx's and I add them up. The total distance is the integral of dx. But of course, dx is just velocity times dt. And the velocity for our oscillating object is a omega cosine omega t. So we plug that in there, and that is then the position. The position is just the integral of a omega cosine omega t dt. Well, the a and the omega are constants. They come out of the integral. And now I'm going to do a u substitution. All right, so I'm going to let u equal omega t. That means that du dt is omega, which means that dt is du over omega. So in my integral, I'm going to replace omega t with u, and I'm going to replace dt with du over omega. And so there's the integral I'm doing now. The omega is just a constant, it cancels out, and then I just have the integral of cosine u du, which is sine u plus a constant. So my position then is a sine omega t plus a constant. Why plus a constant? Well, if I know the velocity at any given time, where I am at any given time depends on where I started, right? So the red curve here is the velocity. These blue curves are a sine omega t plus a constant. So the original curve we had started at 0, but if I start at some other position and have that same velocity, when I integrate that, I will oscillate offset from what I had before. So you can get the position by integrating the velocity to within an additive constant. Now, acceleration is similar. So velocity is the rate of position change with respect to time. Acceleration is the rate of velocity change per unit time. The average velocity is just how much the velocity changes divided by the time it took. And if you take the limit as delta t goes to 0, you're going to get the instantaneous acceleration, which is the derivative of the velocity. But since the velocity is just the derivative of x with respect to t, acceleration is also the second derivative of x with respect to time. So it's the first derivative of velocity or the second derivative of x with respect to time. They're the same thing. So let's imagine a car is moving according to this graph below. At what times is it moving forward, and at what times is it moving backwards? So here, where the distance is positive, that means that the car is to the plus side of where it started. And over here, the car is at the negative side of where it started. But whether the position is positive or negative does not tell me whether the velocity is positive or negative. The velocity is how fast position is changing with time. So right here, the car with time is moving further away. And then right here, it stops and it starts moving backwards. Right here, it goes forward for just a little bit, and then it turns and it goes backwards again. So the places where the velocity is positive are the places where the slope of the position is positive. The places where the velocity is negative are the places where the slope of the position with respect to time is negative. Now, at what times is the car going slow? At what time is it going fast? At what times is it stopped? Well, it's moving fast when the slope of the line is big. So it's big there, it's big there, it's big there. So that's where the car is moving fast. Here where the slope is shallower and here where the slope is shallower, the car is moving slowly. Now, where is the car stopped? So as the car turns around here, right? Momentarily, just for an instant, the velocity goes to 0. And here, the velocity goes to 0. Whenever the slope of position is 0, that's where the velocity is 0. Now, where is the velocity increasing and where is it decreasing? All right, we see right here the car's position is changing with time, but it's changing less and less with time. So as that slope flattens out, that means the velocity is going down. All right? Over here, the car stops and then it starts to go backwards. So the velocity is now increasing in the negative direction, which we would call the velocity decreasing, right? The velocity is going negative, all right? But then the velocity starts to change, right? It's still going backwards, but it's going backwards less fast. So a less negative velocity is increasing in the positive direction. So the places where the velocity are increasing is just right here. We have a negative velocity, but it's getting less and less negative. Everywhere else, the velocity is decreasing or becoming more negative, all right? Now, at what times is the magnitude of the velocity increasing? Well, the velocity is big here because the slope is big, but then it gets smaller and goes to 0. But then it starts moving backwards. As that slope gets steeper, that means the velocity is increasing. But then when we get to right about this point, the slope starts to curve the other way. It gets less slopey, and the velocity slows down. And then we get right here, and then, oh, look, right here, the velocity speeds up a little bit, and then it slows down, comes to a stop, and then it starts to speed up again. So now let's add a plot of velocity to our curve. We can, if I know the function for x, I can take the derivative of it and get the velocity. So I did that. So here's our blue curve again, here's our position, but now I've added with the red line the velocity that I calculated. And once again, at what times is the car moving forward or backwards? We said they're the times when the slope of the blue line is upward, but notice the times when the slope of the blue line is upward is also, those are the times when the velocity is positive, right? That's when it's moving forward. When the velocity is negative, that's when it's moving backwards, and that's when the slope of the position is downward, right? Now, at what times is it going fast? It's going fast when the velocity is big, right? When the magnitude of the velocity is big. So here and here and here. And we also said, oh, it's when the slope of position is big, all right? So the slope of the position being big means the magnitude of the velocity being big. All right, and when is it stopped? We said it stopped when the slope of position is 0, but those are precisely the times when the velocity is 0. Now, at what times is the velocity increasing and at what times is it decreasing? So the velocity is decreasing here, and then it's increasing here, right? So here, once again, we said, oh, look, the velocity is going down. Now it's increasing in the negative direction, which we could call decreasing velocity in terms of when we take signs into account. And then it gets less negative, so we would call that an increasing velocity, and so forth. So that's where the velocity is increasing. Now, at what times is the magnitude of the velocity increasing? We said the magnitude of the velocity was going down here, but when the curve gets more steep, it's going up here, right? Because the curve's getting more steep, all right? And then the curve's getting less steep. That means the magnitude of the velocity is going down. Well, look, the magnitude of the velocity is going up whenever the red curve is moving away from the axis. And that's the same thing as the places where the position's slope gets steeper. I can also calculate the acceleration, right? By taking the second derivative of x or the first derivative of velocity with respect to time. So I've put that onto my graph. So green is the acceleration, right? At time t equals 0, the car is stopped. Well, it's not stopped. It's at x equals 0, and it's moving at some velocity. But notice the velocity is not changing here. The curvature of the velocity is 0. It's flat. So that means the acceleration is 0. So the acceleration tells me how the velocity changes. All right? When the acceleration goes to 0, that's when the velocity is not changing. All right? So at what times is the velocity decreasing? That's when the acceleration is negative. It's increasing when the acceleration is positive. So here's where the acceleration is positive, and that's when velocity is increasing, right? If you take the next derivative, you get what's known as the jerk, and you can take different derivatives. You can keep going. They become less and less useful in most situations. The ones that we care about most are position, velocity, and acceleration. Now, what is the velocity when the position is at its maximum? So at the maximum, that's right when it's turning around and the velocity is 0. All right? What's the acceleration? What's the acceleration when the position is at its maximum? Notice that the fact that my position is at a maximum does not say much about my acceleration, right? So when my position is at its maximum, that's when my velocity is 0. But the acceleration could be anything, right? The rate of change of my velocity could be whatever. Now, let's just do some examples of playing around with position, velocity, and acceleration. Later, in a few days, we're going to talk about what happens when something moves under constant acceleration. So let's just take a preview of that. So let's imagine I throw something, all right? I throw it up into the air, and I see how its height changes with time. Well, near to the Earth, the acceleration due to gravity is constant. It's just minus g, where g is a constant. If I know that the acceleration is minus g, what will be the velocity of the object as a function of time? If the acceleration is constant negative g for all time, how would I find the velocity at all time? Well, remember, acceleration is the derivative velocity with time. So a little change in velocity is acceleration times a little change in time. And velocity is just the integral of d velocity, which we just said is acceleration times dt. And acceleration is just a constant, right? It's just negative g. So I'll throw that into my integral. I know how to do that integral. The integral of a constant times dt is just that constant times t plus a constant, all right? So the integral of negative g dt is just negative gt plus some constant. What is that constant? Well, at time t equals 0, negative gt goes to 0, and my velocity is just that constant. So that constant must be the velocity at time t equals 0. So we'll call that constant v sub naught, and then v is just v sub naught minus gt. So now, if I know that the acceleration is just a constant, negative g, my velocity is just my initial velocity, my velocity at time t equals 0, minus g times t. Well, if I know the velocity, I should be able to find the position as well, right? Okay, so the position, the velocity is just the derivative of position with respect to time. That means that dx equals v times dt. I can integrate dx to get x, but dx is just v dt, and v is just v naught minus gt dt. And I know how to integrate that. That's just going to be v naught t minus 1/2 gt squared plus a constant. What's that constant? Well, when I plug t equals 0 in, I find that x is equal to c. So c must be the position at time t equals 0. I'll call that x naught. And there's x. All right, so I can plot these things. So when I throw something up in the air, I throw a ball up into the air, if I ignore drag, right, the blue line here is how high the ball is as a function of time. And initially it's going upwards, it comes to a stop, and then it comes downwards, all right? The velocity is increasingly downward. It starts at a positive velocity and linearly goes to a negative velocity. When the ball reaches its highest point, that is when the velocity is 0. But notice when the ball is at its highest point, the velocity is 0, but the acceleration is still negative g, right? The acceleration is constant. That's what we started with. Just because the velocity is 0 doesn't mean the acceleration is 0. The acceleration is how fast the velocity is changing. Right here, the velocity is 0, but it's changing. It's going to keep going down because gravity is going to then accelerate our object downward. Now, position, velocity, and acceleration can be vectors if things move in multiple dimensions. So the position of an object I can give just by giving its x, its y, I'm recording right now, and its z components. So I can write the position of, a car or a ball or something as just some function in the x direction plus some function in the y direction plus some function in the z direction. Velocity likewise can be a vector. All right, and how do I find the velocity vector? Well, velocity is just the derivative of position with respect to time. So that's just the derivative of rx I hat plus ryj hat plus rz k hat. And I know how to take the derivative of a sum of things, right? I just take the derivative of each individual part, and of course I hat, j hat, and k hat are constants, so they come out, and so velocity is just I hat times the derivative of r sub x. J hat is just the derivative of the y component of position, and the x component of velocity is just the derivative of the x component of position. The y component of velocity is just the derivative of the y component of position, and the z component of velocity is just the derivative of the z component of position. So, in other words, Vx is the derivative of Rx, Vy is the derivative of Ry, and Vz is just the derivative of Rz. Acceleration can also be a vector, right? And similarly, the x component of acceleration is just the derivative of the x component of velocity, and the y component is the derivative of the y component, and the z component is the derivative of the z component, and so forth. So now let's do an example of something moving in 2 dimensions. Later on in the course, we're going to talk about motion in circles. So let's get a preview of that. So let's imagine I have a car that's driving at a constant velocity in a circle. Well, all the points in a circle are defined with this equation right here, right? So a point, a distance r from the origin, making an angle theta from the x-axis is just going to be r cosine theta in the I hat direction, in the x direction, plus r sine theta in the y direction. Well, we want that then to change linearly with time, so let's make theta equal to a constant times time, omega times t. So there is the equation for the position of our car at every time as it moves in constant velocity around the circle. Well, what's the velocity vector? Well, if our position vector is this, the velocity vector is just the derivative of that. And the derivative of r cosine omega t, r is a constant, omega is a constant, and using the chain rule, right, we found that the cosine of omega t is just negative omega sine omega t. So I just get negative r omega sine omega t. And when I take the derivative of this, I get r omega cosine omega t. So now I have my vector velocity. And if I look at my car when it's at different positions and I plot the velocity is always at 90 degrees from the displacement. The velocity is tangential to the circle. Now, what is the magnitude of the velocity? Well, it's supposed to be a constant, right? That's what we were shooting for. Well, if I take the magnitude is just the square root of the x component squared plus the y component squared, right? There's the x component, there's the y component. Now, when I square this, the minus sign goes away, and both of these terms have an r squared omega squared, so I can pull them out of the square root, and I'll get r omega times the square root of sine squared plus cosine squared. But sine squared plus cosine squared is 1. So the velocity is just r times omega. Hey, r and omega are constant, so it worked. Our velocity is indeed constant. Well, if I know the velocity, I can find the acceleration by taking the derivative of the velocity, right? And since our velocity is this, we take the derivative of this, we get out another omega, sine becomes cosine, bring out another omega, cosine becomes negative sine, and there's our acceleration. Notice that that is just omega squared, negative omega squared times r, right? The x component of our acceleration is just negative omega squared times r cosine omega t, but that was the x component of position. The y component of acceleration is just negative omega squared times r sine theta, but r sine theta was just the position, right? Yeah? And so acceleration vector is just minus omega squared times the position vector. Pretty groovy, huh? So that means, that minus sign means that the acceleration is pointed in the opposite direction from the position, from the displacement of the object from the origin. That means that at every point, the acceleration is in towards the center of the circle, as depicted with the green arrows. Now, what is the magnitude of the acceleration? Well, it's just omega squared times the magnitude of r, right? And the magnitude of r is r. So there's the magnitude of acceleration, omega squared r. But we can remember that the magnitude of the velocity is just r times omega. So I can solve this. I can say, oh, r is just v over omega. That means the acceleration is also equal to omega times v. Or I could say, look, omega is v over r. I plug that in there and I get that acceleration is v squared over r. So that's something we'll use later in the semester, but we've just derived it right now. If something moves in a circle at a constant velocity, the acceleration has to be inward, and it has to be equal to v squared over r. Groovy. So that's the end of our discussion of acceleration and velocity. I hope that's given you some intuition and some tools to help you work with them.